We can apply the same arrow pushing strategy we used with resonance to acid-base reactions and most reactions in organic chemistry. So let's talk about basic Bronsted-Lowry acid theory. A Bronsted-Lowry acid is going to be a proton donor, meaning we have an extra hydrogen somewhere in the molecule. In this case, this is HA, that's our acid. A base is a proton acceptor. Typically, it's going to have a negative charge or a lone pair. So, after the acid-base reaction, the base picks up a proton and becomes the conjugate acid, because now it can do the reverse reaction and give up that proton. The acid becomes the conjugate base, because now it can pick up the proton from the conjugate acid. This is all review from Gen Chem, but how do we do this in organic chemistry? Well, this lone pair of electrons will be attracted to the proton of our acid, because typically acids are electron withdrawing, so that hydrogen atom is going to have a partial positive charge. If we're making a new bond with this double-headed arrow, this bond needs to break. What happens here is the electron density gets shifted to make a new lone pair on the conjugate base. We can do this reaction backwards as well. The conjugate base can attack the proton of the conjugate acid. This will break the bond between the base and the hydrogen, and we'll get the left side of the reaction again. Let's apply this to some actual molecules. Say we have acetic acid and hydroxide. You should recognize that hydroxide is a very strong base. Why is it a strong base? Well, it has a negative charge. And remember, atoms don't like charge. We've got 3 lone pairs here. We need a proton donor. That's going to be the acetic acid. Here's our proton. The base will be attracted to the proton. This will break the bond and shift the electron density onto the oxygen. So here's our acid. Here's our base. Let's progress a little bit. This will leave us with a negative charge on what was our acid and is now our conjugate base. And it's going to result in the formation of water, which now is our conjugate acid. In the reverse reaction, the oxygen of the conjugate base can be attracted to the hydrogen of water. One more example, if we take pyridine and hydrochloric acid. First off, let's draw the lone pair on this nitrogen. We have a lone pair right here, which means this is going to be our base. We have an extra proton right here. This is going to be our acid. The base will be attracted to the proton. When it forms a new bond, we're going to break the bond between the hydrogen and the chlorine. This results in the formation of pyridinium. It's going to be our conjugate acid, and the chloride ion, which is going to be our conjugate base. If we do the reverse reaction, the chloride would be attracted to the proton, which will give the lone pair back to the pyridine.